Okay, hi guys. So there was some technical glitch. We have started this new stream for the 1 minute. Voice is not coming. I think everything is fine from my side. Okay, I think my everything is fine from my side. The voice should come. Prashant, I okay. Thank you, Sumit. Thank you, Karthik. Okay, so we were discussing key. Why do we how do we compute the complexities and why should we check complexity before anything, before coding any solution? Okay, so let us go back to what we have started. Okay, so this is what we have started few times back. Now, okay, so today's agenda is number theory, and as I was telling that to find the factorial of a number is something that anybody can do. Okay, we do not have to think anything much greater thing. What we can simply do is we can take in a function, take n inside it, and then what we can do is we can generate a loop from I to I less than equal to n, I plus plus, and what we can do is we can compute the product, which is product into I, and this product should be initially initialized to 1. This will can be an integer, and then we can return the product. This is how we can compute the we can limit the range by reducing the number of loops. Yes, that is one kind of a thing. Okay, but that is well, every time we are not trying to reduce the number of loop. There are different things. That is what problem solving is. Okay, so now this is a easy task. We can compute what is the factorial of a number. Okay, using some sort of algorithm like this. What I am asking here is 5 factorial is you can also use recursion for that. 5 factorial is 120. What the question out here is, just start looking from the right side, start counting from the right side, and if the factorial value has zeros, has trailing zeros, what you do is return the count of the zeros. Suppose the 5 factorial is 120. I look from right, it has trailing zeros, I count. The count is 1, so I return the value of 1. So what I am asking is, what is the trailing zeros in the factorial of a number? Now what you can do is you can use this particular algorithm to find the factorial of the number. Once you have the number, you can iterate using a loop and count zeros. But let's suppose that number is a big number. I'm not computing the factorial of 5. So let's suppose I'm computing the factorial of 253. Let's say I'm computing the factorial of 253. You can use your calculators. I'm very much sure that your calculators will fail to calculate this factorial value. Why? Because we are storing the factorial as a int value, and if your fundamentals are good, you might as well know that int has a range. I think that range is around 10 to the power 9 digits or something of that sort. Something bigger than int is a long, which has nothing but 10 to the power 18. This is the limit. This is the range of the number of digits that it can store. Let us suppose that we have a number that is exceeding both of them. Okay, and if it is exceeding both of them, then just using a loop to count from right, using the algorithm that we discussed here, and then return the number of zeros will be a very Herculean task to do. So what we are interested here is not in using a brute force. What we are discussing here is a brute force solution. What is a brute force solution? A brute force solution is a solution that gives the answer. It is an algorithm that gives the solution, fine, but takes longer time and generally exceeds this criteria of 10 to the power 8 operations per second. And we will generally get a TLE with a brute force approach. But why is a brute force approach necessary? Brute force approach gives us a get going. We know that this is a solution that we can think of, and this exceeds 10 to the power 8 operations per second. So we have to perform better than the solution. And we have a solution that gives the answer. So at least we are eliminating the wrong answers out here. We are in the path of accepted solutions. Just we have to neglect the TLEs. And this is what we must do. We must always think of a brute force solution, and then we will move forward with some solutions. Okay. Now, if we are dealing with number theory out here, as I told you, so this is what is the use of number theory. Number theory gives us some operations, some fundamentals, some concepts that help us to solve such kind of tasks. Okay, where we have to reduce our TLEs, okay, 10 to the power 8 operations. So some fundamentals of mathematics that we have studied in our early years, or we might have missed them. We called them tricks while solving our basic problems. We all use these things out here in our DSA or coding to execute operations that are less than 10 to the power 8 operations per second. So while dealing with this question, what was the question? Simple question: find the number of trailing zeros in factorial of a number, and supposedly this number is a large number. Okay, so what we can do, think of it for a while. Anybody? Convert factorial into string, then reverse it using division, and can be any number. Then how to find zeros? Then use counter reverse. Okay, so I am getting some solutions in the comment box. Somebody is saying he find the factorial of the number, then reverse the number, and then count the zeros from the front. Again, the problem is the same. Why I will reverse the number? Suppose I have a number like this. Why I can always start a loop from this side. The problem here is that I am not able to store this number in int or long. Okay, if n is large, I'm not being able to store this number. Okay, Soham Dabani has given an answer check for multiples of 2 and 5. Okay, this is the solution. So, and somebody is telling use modulo operator. See, modulo operator will reduce the number, but it will also eliminate the number of zeros. If the number is 120, I use a modulo with suppose 6. What will be the answer? Answer will be 0, because modulo reduces the number. Suppose it is not 6. Suppose I am taking a modulo with 9. What will be the answer here? It can be anything, but it will not be equal to 120. Okay, and if I compute the factorial of this number, I do not have any properties in modulo operator where original factorial can be retrieved by after the reduced number, after finding the reduced number. So we cannot use the modulo operator. One thing is what we can do is, just look here. If I am computing 120 factorial, okay, if I am computing 120 factorial, let me just reduce it a bit smaller, take a smaller number out here. I will not take 120, it will be a lot to compute it. Let's suppose I am taking 5 factorial, for example. Okay, so what is 5 factorial? 1 into 2 into 3 into 4 into 5. This is how we solve basically. We don't take we take smaller numbers, but try to optimize the algorithm for larger numbers too. Now see, what is this 5 factorial? This comes out to be 120. The number of trailing zeros here is 1. 1 is the answer. Now what we have to look here is from which all components of 5 factorial is responsible for this 0. We can write 120 as what, 12 into 10. We can write 120 as 12 into 10. Okay. Now, from where this 12 comes? I can see that this 12 can come from 4 into 3, from this factorial, from this and this. And from where this 10 comes? This 10 comes from this 2 and this 5. Okay. So, I know I am not interested in other factors of this, other numbers constituting this factorial. I am only interested in 2s and 5s, because every 2 into 5 will give me 110, and every 10 will have 1 0 in it. So if I'm able to just calculate how many 2s and how many 5s are there in the factorial multiplication, this expansion, how many 2s and how many 5s are there, and if I club every 2 with every 5, I will get 110, and this 10 will give me 1 trailing 0. Another 2 and 5 will give me another 10, and this will increase the number of trailing zeros to 2. Another one will give me another 10. This will increase the number of zeros by 3. So what am I now interested in is the number of 2s and number of 5s in my expansion of this polynomial, of this factorial. Now, if I look closely, I am looking for 2s and 5s, but 2 is also here. This 4 also has 2, but none of these 2s are responsible for the 10. Only these 2 is responsible for 10. So if I have, suppose, 10 2s in an factorial, all the 10 2s are not responsible for giving me a trailing 0. Only some of them are responsible. And who are those 2s? Which 2s can be clubbed with 5? Okay. And what I can see is every 5 when multiplied with a 2 will give me a trailing 0. So what we can say here is, instead of counting 2s and 5s, what we can do is, I will only count the number of 5s in a given factorial. Why? Because this 5s when clubbed with 2s will give me trailing zeros. Okay. So what I have to do is, I just have to divide. If I have to compute number of trailing zeros in n factorial, what I will do is, I'll divide my n by 5. This will tell me how many 5s are there in my n. Suppose in the given question, I have 5 factorial. What I do is, I divide 5 by 5. I get 1. So I get here, I have 1 5 here, and this 1 5 is responsible for the trailing 0, and this one is this 0. So by getting this number, this n by 5, whatever this will be, this is the number of 5s and this is also the number of trailing zeros. So the solution comes out to be a O1 solution. What we have to just do is we have to compute a variable named d, get n by 5 and get the floor of this. Why floor? Because suppose n is 26. If I divide 26 by 5, what I will get? I will get something like 5 5s are 25.2. I'm not interested in this 0.2. I'm only interested in the decimal part. The integer part, sorry. The integer part. That is why what we will take is the floor of n by 5 and whatever value gets stored in this d, we will return it. We will return it. This will be our trailing zeros. Okay. Why not counting 2? We are not counting 2 because all 2s are not responsible for trailing zeros, and only those 2s are responsible for trailing zeros which get multiplied by 5. So if only those 2s are responsible for getting trailing zeros when they are multiplied with 5, so counting the number of 5s or counting the number of 2s that get multiplied by 5, both are the same thing. That is why we get 5. We only take 5. Okay, do we have any simple approach? This is one of the simplest approaches here. Just understand here. It is mathematics. That is why we are taking. It is taking a bit complex to understand, or I am not being able to make you understand it properly. Okay, let me try once again. See, what we are getting here is 5 factorial is 120. It has one trailing zero. The answer should be 1. Now, what are we interested in is from where this 0 comes. This 0 will come from 2 into 5. Okay, 2 into 5 is 10. So, if we get key 5 factorial के expansion में, how many 2 into 5s are there? How many 2s are there? How many 5s are there? So, that this number will give us the number of trailing zeros, because the number of 2 into 5s are there is equal to number of tens that will be there, and if we have the number of tens are nothing but number of zeros. This is what we want. Now when we need to count 2s and 5s, we can count only 5, because all 2s are never responsible for giving us 10, but every 5 present in the factorial is responsible for a 10. That is why we are only counting 5. Okay, and how can we get the number of 5s in the expansion of any factorial? We will just divide this by n by 5. Okay, now one more criticality is there. Suppose I am dealing with any number that is greater than 25. I want to get 26 factorial. Then what will be the multiplication numbers out here? 1 into 2 into something 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 20 something 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 25 into 26. We are getting this. Now till here the n by 5 works, but 25 is itself 5 into 5. Okay, why did we eliminate number of 2s? Because every 2 was not responsible for giving us a 10, but every 5 was responsible for giving us a 10. That's why we were taking only number of 5s. But if the number is greater than 25, what we are getting here is 25 is itself made up of 2 5s, and only one of these 5 can give us a 10. Both of them cannot give us a 10. So n by 5 will never work here, because if we will give n by 5 here, what we will get is number of trailing zeros plus 1, because we will get one more extra 5 here which is not responsible for the 10. Only one of the 5s from here is responsible for the 10. So what we can do here is, for numbers less than 5, we will divide it by 5. To eliminate this thing, what we will do is we will divide it by 25. Then again, what will be the next thing? Next thing will be 125, and so on. So what we will do is we will check what is the size of an n. If n is greater than 25, then we will use these two things. If n is greater than 125, we'll also add one more thing here and just find the floor of these values, and we will get an answer in O of 1. We do not need to run any loop out here. Okay, we do not have to consider any loop. We just have a value. We will input n, we will get the n, we will find whether n is less than 25 or greater than 25, less than 125 or greater than 125. We will just find a value d, which will be n by 5 plus n by 25 plus n by 125 and so on. Find the floor of every value. As we are not interested in the decimal point, return this d. This operation is a mathematical operation which takes O of 1. This also takes a constant time. This also takes a constant time. This takes a constant time. The overall complexity is also a constant operation. So whichever be the number, even if the number is something like this factorial, then also we will execute this in O of 1 time. Okay. So this is how we compute the number of trailing zeros. Any doubt till here? Okay. Anybody has any doubt till here? Let me solve it with using one example. Okay. Suppose I want to calculate number of trailing zeros in 10 factorial. Okay. What we do? We compute 10 by 5, take the lower of it, floor of it. This comes out to be 2. Okay. Now we use a calculator to solve 100 factorial. Okay, let me use Google for it. Okay. I think the screen will be visible to you all. Okay, just look here. Just look. N factorial is nothing but 3,628,800, and the number of trailing zeros here is 2. Okay. Now let us take one more example. Suppose I want to calculate the number of trailing zeros inside say 255 factorial. Okay, what we can do here is 255 by 5 plus 255 by 25 plus 255 by 125 plus 255 by 5 4. What is 5 4? Comes out to be 625, and as 625 is greater than 255, we will not consider this thing. So we will only deal till here. Now compute the values, individual values. What is 255 by 5? $255 by 5 comes out to be 51. Now, what is 255 by 25? Comes out to be 10. Then what is 255 by 125? Comes out to be 2. Add this. What is this? This is 63. So 255 factorial will have 63 trailing zeros inside it. Okay. How do we verify it? I think Google may be able to answer us. Let us check. What was the number? 255. Okay. So 255 factorial. So this is the factorial of 255 out here. Okay. And if anybody is interested, he or she can count the number of trailing zeros. The trailing zeros start from here. Okay. These are the number of trailing zeros. Okay. So each line has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 zeros. 12, 1, 2, 3, 4, 5. 12 5 is 60, 62, and 63. We have our answer. So what we come to know here is that our algorithm is giving 63 trailing zeros, and 255 factorial according to Google also has 63 trailing zeros. So this is what I was discussing. This is what the algorithm is. What we have to do is we just have to count the number of fives inside the number of fives in a number, okay, and move on with 5 power 1, 5 power 2, 5 power 3 until the number gets. Yes, yes, same logic we can write in the program. Okay, I am just implementing this program. Okay, just I am implementing this. Okay. So guys, this is the implementation. Okay, why not count 2? Because every 2 is not responsible for 10, but every 5 is responsible for a 10. Simple logic. So this is the implementation. Okay, let me first run this program for you all. Okay. Okay. Now, I think this is visible. Yes, this is visible. Okay. Okay. This is the program out here. Okay. Now, I'm just running it. Okay. It is asking for an input. Okay. Oh, I understood what is happening here. I have given it a value of 255. That was our test case out here, and it is returning at the number of trailing zeros is 63. Now, how is it working? How is it working? Can anybody guess? See, this is bit slash std. This is just an input. Okay. Now, this is the function out here. If Rn is less than 0, if Rn is less than 0, okay. So everybody knows that factorial is only defined for positive numbers. So that is why I'm returning a -1 here. Now I'm initializing a count to 0. Then making a for loop that starts from 5. Okay. Then I'm dividing my n by this 5. Okay. N by I is nothing but n by 5. And till this n by I, which is 5 by 5 by 25 by 125 and so on, will be equal to greater than or equal to 1, then only a loop will execute, and I am increasing my I by multiplying it with a 5. So if it is 5 now, again it will be 5 into 5, 25, then it will be 5 into 25 into 5, it will be 125. So I am handling all these cases in the for loop statements itself, and for every iteration, whenever the iteration is console is entering the loop, that's what does it mean? It means that n by the dividing factor is greater than 1, and if it is greater than equal to 1, we have our answer. So we are adding it with the count value, and finally I'm returning the count as discussed earlier. Okay, so now moving on to the next topic of today. Okay, now the next topic, I think this is clear for everybody. So the next topic is Eratosthenes. Some spelling is there. What is this spelling? Okay, so the spelling is Eratosthenes. What is Sieve of Eratosthenes? Sieve of Eratosthenes is a very unique and a very promising algorithm or topic of number theory that is highly useful in solving competitive programming questions or any company questions that are related to this topic, this simple topic, prime numbers. Okay, if I tell you to check whether a number, check whether 5 is a prime or not, what we do in general, we go by the rule of property of prime numbers, that prime numbers are what are the numbers below 5? 1, 2, 3, 4 and 5. So 5 is only divisible by two numbers, by 1 and by 5, that is by 1 and by itself, and not any other number that is less than this. By using this property, we can find whether a number is a prime or not. So just using this logic, we can code a function check prime. What is check prime? Suppose we are having a function, a number n. What we can do is we can just start a loop from 2, because I know key once it will be divisible by 1. I can move till Why I cross I? There is a logic that says, there's a rule that says that prime numbers are, if n is a prime number, okay, then any number that lies between 1 to root n, okay, it is only divisible by 1. It is any prime number is only divisible by only one number in the range of 1, say root n. That is why we are taking I cross I into I is less than n. This comes out to be nothing but I is less than root n. And if I divide our n by I and it comes out to be 0, we can say that flag is 1. And what is flag? Flag says ki if flag is 1, say it is not prime. A simple logic. Okay. But same thing, if I tell you ki n ka range is very long, n ka range is something in 10 to the power 8 or 9. Suppose it is in 10 to the power 5s. Okay, largest value of n. And I tell you ki I will give you two numbers, say A and B, and just tell me the number of prime numbers between A and B. One simple logic is you can code a loop from A to B, and inside this loop you can call the above function, check prime function. This is a simple concept. We have already done the check prime function here. So what we can do is, between these two ranges we can call this check prime function. Okay, but what will be the complexity of this function? The complexity of this function will be O of n for this loop into the complexity of the inner function, and the inner function's complexity is what? It also has a loop. And some if-else statement, so we can consider it as constant. So we can tell that this has a O of n complexity. Okay, so the final complexity to find numbers in a loop comes out to be O of n into n, which is nothing but O of n square. Can we optimize this? Yes, we can optimize it. Check prime function once more. Okay, what we are doing is we are creating a loop from 2 to root n, adhering to this property of prime numbers is ki if any number below the square root of that number and 1, between this range, any prime number is only divisible by 1. Okay, so what I am doing here is I am taking a loop from I equals to 2 to the square of this number, square root of this number, and in this range I know if n is a prime number, then it will not get divided by any of these i's. So if any of these i's divide my n, I set my flag to 1, and at the end I am checking if flag is 1, then print not prime. Okay, this is the simple logic. So we come across key, if we are using this logic to find numbers in a range, we will get a complexity of O of n square. Sieve of Eratosthenes helps us. What Sieve of Eratosthenes tells we will use a pre-processing technique. What we will do is a pre-processing. Before even taking any inputs, what we will do is, it is a simple trick. What we did in our childhood while studying prime numbers, we will list down all the numbers. Suppose we are listing down the numbers from 1 to 20. Okay, now we know that 1 is not a prime number, not a composite number. We eliminate this. Now we take the first number 2 and delete all the multiples of 2. I think you all might remember this process. Now, then again we take 3 and delete all the multiples of 3. And we proceed so on. And at the end of this process, all the numbers that we had encircled were the prime numbers. So what we do is we first compute the prime numbers between a range 1 to n. Okay, and we store them in an array as whether this number is a prime, false, whether this number is a prime, yes, it is a prime, whether this number is prime. Yes, this is prime. Whether 4 is prime, no, it is not prime. So we store an array like this. And whenever we have to find whether any number is prime or not, what we do is we just go into, suppose I have key if 5 is prime or not. What I will do is I will go to the 5th index of my array and check whether it is true or false. If it is true, then the number is prime. If it is false, then the number is not prime. As simple as that. And checking this takes O of 1 time. What was O of n square to check a number if it is a prime or not comes out to be O of 1. As simple as that. Sorry. O of n. So we have reduced the complexity from O of n to O of 1 just by using a pre-processing. By storing whether the numbers in a given range are prime or not as false and trues, and just whenever we have to check whether a number is prime or not, what we do is we index that array to that number and check that at that index the value is true or the value is false. If the value is true, we give the number is prime. If it is false, we give the number is not prime in O of 1. Okay, you can store anything. We don't store in the dictionary. Or dictionary is not there in C++. So how will we do this? What we do is we first take the largest possible n out here and initialize an array of size n plus 1. We initialize a size array of size n plus 1. Suppose we have to take the find the numbers, prime numbers in the first 10 numbers, first 10 natural numbers, who all are prime numbers. So what we will do is we will initialize an array of size 11, 10 plus 1. Okay, as we all know that array indexing starts from 0. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is an array of size 11. By default 0 is not a prime number, not a composite number. So what we will do is we will already set this as false. By de facto, we will set this as false. And if you will remember, what we did in this technique was initially every number was visible. Not a single number was cut through. Okay, there were not circles and no cut throughs visible. So same thing we will do is we will initialize every number as true. Every number as true. Then we will start and 1 should always be false because 1 is not a prime number, not a composite number. So 0 and 1 should be false. So what we do now is we start from the first number that is true. First number that is true, which is 2, and then iterate over every multiple of 2 and check whether it is true or false. If it is true, we change it to false. We change it to false. We change it to false, and so on. Similarly, after every number is converted to false, we check in an array which next number is true. We come across that 3 is now true. So what we will do is we will iterate to every multiple of 3, and if it is false, then okay. But if it is true, then what we will do is we will change this to status to false, and so on and so forth. Now the next number is 4, but it is already false, so we will not proceed with it. The next iteration we get 5, and 5 we have the status as true. So what we will do is we will again move forward with every multiple of 5 and check their status. If the status is true, we will convert it to false. If it is false, then it's okay. At the end of this iteration, what will happen is all the prime numbers will have their status as true and all the composite numbers will have their status as false. As simple as that. And whenever we will have to check whether a number is true or false, what we will do is we will just suppose we have to check whether 6 is a prime or not. So what we will do is we will just index till 6, check its status. The status is false, so we will return that 6 is not prime. Suppose the question asked here is, I will give you a range. Suppose the range is 3 to 11. Print all the prime numbers within this range. Okay. Before we were using that algorithm, which was giving a complexity of O of n square. One to iterate from 3 to 11, another n to check whether the number is prime or not. Okay. Now here, what we will do is, when we have stored this array as a pre-processing step, what we will do is we will just iterate from 3 to 11, which takes O of n time. Okay, and while iterating itself, what we will check is what is the status of that array, that index, whether it is true or false. If the status is true, we will print that number. If the status is false, we will not print that number. So we just have to traverse this range, which takes O of n time. So we have reduced the complexity from O of n square to O of n. Okay, we are only dealing with the traversing part. For checking the prime number, we have already stored this. Okay, so the only complexity that we are concerned here is the complexity that will be required to create this sieve. And to create this sieve, the complexity will be log of n, which is very low. So the entire complexity of checking numbers in a range comes out to be O of n into log of n, which is very much lower than O of n square. So this is what is the beauty of Sieve of Eratosthenes. Okay, now any doubt till here? Now for the C++ implementation. Okay, let me explain the code to you first. Okay, so what I'm doing here is first creating a function for named Sieve of Eratosthenes. Eratosthenes, whatever it is called. It is a function. This is a driver function. What I am doing here is first what I told you. If I have to find numbers in a range of n, so what we do is we create an array of size n plus 1, adhering to the fact that array indexing starts from 0. So this is what I have done. I have created a Boolean array named prime of size n plus 1 here. Next what we do is we initialized everything as true. and 0 and 1th position as false. So this is what we are doing. We are using memset function, memset from C++, which has a property that if memset is given to anything, here it is a value and this is the size. Okay, so what is memset does is it initializes every element of this thing, this structure, with this value up to this size. This is what memset does. So what I have told memset to do is take the array prime, assign true to every element of it. Okay, this is what it is doing. Now what I am doing is I am taking a loop from 2 till root of n. Okay, and if that index status is still true, what I am doing is I am making it if the status is true, I am iterating to every possible multiple of that number and changing the status to false. Okay, and outside of this loop I am again starting from 2 to the end of the numbers. I am just printing every pre. This is what we discussed here, okay, as an algorithm, and this is what is the code of it. One thing I have not mentioned here is that we have to make prime 0 and prime 1 as false, but this thing is taken care when I am using p equals to 2. We are not starting from p equals to 0. Okay, any doubts still here? Okay, how log n for Sieve of Eratosthenes? Okay, just what we are doing. If I am having n, first I am dividing n by 2, then I am dividing n by 3, then I am dividing n by 5, next prime number, then I am dividing n by the next prime number 7, and so on. So this comes out to be a harmonic series, and what we can do is we can take n outside of it, and this will become 1 by 2 plus 1 by 3 plus 1 by 5 plus 1 by 7. And this harmonic series, you can just Google it. This harmonic series has a sum of log n, and thus n log n comes here. Okay. Now, the next topic of today was modular arithmetic. Okay. So guys, so we end this session today here. Okay, you can join the Discord server and the Telegram group. The links are in the description box. Okay, and everything right from the practice sets, practice questions, everything will be there. You can ask your questions, doubts directly in the group. Okay, and we are there to help you. See you tomorrow.